Welcome back. This is Larry Benko, W0QE, and this video is about one of the most useful calculations that SimSmith can make, and is also one of the most common questions I receive. Perhaps you have just purchased a new VNA, like the Nano VNA, watched a few of my videos, and wish to understand more about RF. SimSmith, and especially SimSmith coupled with a VNA, can be great for helping to understand many RF topics. This email was received a few days ago and is shown here with the permission of the author, whose last name and call sign suffix have been removed. I've covered all these topics in previous videos, but either I haven't explained them clearly enough or they are not that easy to understand. Joe's email indicates that he wants to analyze the matching range of the MFJ-933 over frequency and then see what sizes of loop antennas would be compatible with this tuner versus frequency. This example showcases the capabilities of SimSmith, and I will try to explain these steps more clearly. Shown here is a schematic of the MFJ-933, which is a capacitor-only matching network. Capacitor-only networks have the advantage of using higher Q components, which results in better efficiency for matching small antennas, but they have the disadvantage of having a smaller matching range. The schematic shows what appears to be a differential capacitor, but I believe it is actually a ganged capacitor. Analyzing the circuit with either topology is easy to do, and we can see if one topology is better than the other. Let's begin with a blank SimSmith circuit, and I will slowly build up the circuit of the MFJ-933, showing what its matching range is. File, New Circuit gives us a blank circuit. There's nothing in the plot window here, and we get a default generator type, default load type, which is 50 ohms. We can change these if we want to. We don't need to change them in this case. And we're going to put our matching network in here. Let's put a matching network in here right now, and we'll put it in a, we'll do it in a ruse block. It really doesn't matter how we do it. And what we will put in this ruse block is a really simple matching network. It's just a resistor. And we will make that resistor 10 ohms. Now, if we choose to make it 10 ohms here, directly on the component, we don't see a parameter here. If we choose to want to make the value of R1 set in the parameter fields here, we just leave it as a dash, or we give it a name. We could have given it a name like, say, R1 V. That would be okay. And we would have a variable that we could set, and we could set that to be 10 ohms. But what we have now here is basically a 10 ohm resistor is our matching network. Now you might say, well, that's a stupid matching network because it's lossy, and you'd be correct, but what we're trying to show here is how SimSmith works. So just bear with me. We have a 10 ohm resistor here. So if we want to look at the impedances at various places, we can sweep SimSmith. We're going to look, we're looking from the generator here back this way, and let's turn everything off. And what do we see? We are going to sweep versus frequency, and we can change what frequency we sweep at. We're sweeping over. We're going to look at the load. And what do we see for the load? Well, we see this pink dot, 50 ohms. Well, 50 ohms is what the load was. The load didn't change. This could be a file we loaded. We'd see a sweep here of what the file values were versus frequency, but in this case, it's a fixed load. We can look at A. That's what we're seeing here. And what do we see? We see 10 ohms more than 50 ohms. We see 60 ohms. I'm not quite on it perfectly, so 60 ohms we see right down here. And if we look at G, we also see 60 ohms. The G is kind of an interesting thing to be able to look at. We're looking at this side of the generator when we're doing that. So we're actually looking at G.Zn. We have several things we can look at. At this point, we can look at A.Z, capital Z, which is the impedance looking this direction. We can look at A.Zn, which is impedance from here looking this direction. SimSmith has a lot of different little ways to look at an impedance. We also have ways to look backwards. And let's plot a couple of those. Now, SimSmith gives us these choices by default, but we can add anything we want to. And there's been discussion over the years as to which things SimSmith should include and not include. And if you let everybody have their choice, there would be so many down here that it would be ridiculous. So the choice has been to give just a few and let people add their own. So I'm going to add some here. Here's 6 more I added. Now there's an error here. So we look at, and these are, since they're separated by a semicolon, they could be on different lines. It wouldn't matter. I just chose to put 2 of them on a line. Smith, so we're going to plot on the Smith chart, L dot ZN. That means we're going to look at this side of the load looking that direction. Well, that doesn't make any sense. That's why SimSmith doesn't allow it. So let's get rid of that one. Now, Smith, A dot Z, that's looking right here, looking this direction, what impedance we see. Smith, A dot ZN, that's looking right here, looking this direction, what do we see? Smith, G dot Z, that would be looking over here, looking this way, and it doesn't make any sense to look at the generator on the other side of something that's internal to the generator, so SimSmith doesn't allow that one either. And then we have Smith of G dot ZN, which is this side of the generator, looking to the left. And let's look at those real quickly. And the order at which SimSmith plots these things determines which one shows because it takes them in order. So let's plot nothing. Start at the beginning. L dot Z, 50 ohms. Look right here. We're looking this direction, 50 ohms. A dot Z, we're right here, looking this direction. We should see 60 ohms. We do. Right there. Then we see A dot ZN. Well, that's right over here. That should look like L dot Z. Let's see if that's the case. It is. Let's change its color to be something different. We see it there. And G.Zn should look like A.Z. And let's plot G.Zn, and it's 60 ohms also. So you might say, well, that's really nice. But that's not what I want to do. What I want to do is ask the question of when I have a specific value set in my matching network, what would give me 50 ohms back here? Well, there's another thing we can plot. And what we can plot is L dot INV Z and that's another thing to plot. So now let's add that one. And let's change what we're going to plot. Its color. Make it dark, make it say dark green. And we plot that, we see a value of 40 ohms. Now, does that make sense? And it makes sense to me because what we're asking is, what value back here would match to 50? Well, since we know this is a 10 ohm value, we see this being 40 ohms. And that did the calculation correct. So let's change this value and watch what happens to this plot. Let's turn all the others off so they don't get in the way. And as we make R get larger, we see that the value back here gets smaller because to get 50 ohms, it's the addition of the 2 of those. And of course, we go this way. And eventually, at some point in time, we're going to run out of the ability to get to 50 ohms. And that's okay, and SimSmith just won't give you an answer. So SimSmith does the calculation correctly. Now all we need to do is manage to put the correct circuit in here and we're good to go. So we can get rid of these things because we really don't need those. And by the way, this is not a list, not a complete list of what we could do. We can look at voltages and currents here. We can look at voltages and currents across the components, and the list is pretty large. We can look at SWRs looking at any point this direction. We can also look at L.REVZ, which is reverse impedance. We look this way looking at impedance. And while we're here, since most of the calculations that a Smith chart type program does starts at the load and calculates impedance going this direction. This is why we have a circuit that typically to most people would seem to be backwards. If this really bothers you greatly, just go View, Backwards Circuit. SimSmith turns everything around and it looks better. I don't think it looks better, but if you think it looks better, then it doesn't make any difference. It does the exact same calculation, so you can change it if you wish. We can get rid of all this stuff. This stuff really doesn't do anything to our calculation. Now the next thing let's do is take this block and let's make this look like our circuit. And this is pretty simple to do. We'll take this resistor right here. We can hold the control key down, click on it, and it'll erase it. If I want this to look a little bit bigger, I can just go anywhere in this part of the circuit and click, or excuse me, scroll the mouse wheel, and it'll get a little bit bigger if we wish. Or you can make it smaller too. And you want to move stuff around, you can grab it and move it. And let's start by putting a capacitor by the generator. Remember, the generator is on this side of the circuit. We're going to get lots of errors as we start to build our circuit up. SimSmith continues to run in real time. It is not a batch program like LTSpice is. And the first thing we're going to do is add the capacitor that connected to the transmitter or the generator. And that was a component we called C-match on the MFJ-933. So let's call it CM. And this is the reference designator. And there's a value. As soon as we put the reference designator in here, SimSmith is going to look for a value for it. It gave us a parameter. We could have put the value here if we'd wanted to. We could have said 2 picofarads, in which case we wouldn't have had a value to change. We could have left it alone with the default right here. SimSmith gave us a choice. It picked a value. It picked a value, not a value. It picked a nomenclature for the value of the component. It was the reference designator with an underscore. We could have called it something else. So let's just go with this one, CM underscore. What I really want to do here, though, is I want to have a Q value on my capacitor also. I want to see the effect on this tuner for Q, because we know we're going to be matching a little antenna, and we're really concerned that the Q might affect our efficiency a lot. So we'll manually say we're going to use the same value for the value of the component, and we're going to set the Q also. This is a constant Q. If we wanted to set the Q at a certain frequency and then let Q vary with frequency due to the fact that the reactance varies inversely with frequency, we could have done it Q and then space and a frequency if you'd measured the Q at a certain frequency. I've discussed that in other videos, but like this is a constant Q. So there's the first component. Now we can either copy this component if we wish, or we can just create a new one. We come in here after we drop this. If we hold our mouse over this and hit R, we rotate it. And let's rotate it and do the same thing, except let's call this one CTA, because what we're doing, this is the capacitor is a tuning capacitor. It's the A section of it. And do the same thing with its value, CTA underscore space Q. And notice we got a CTA. We're going to use the same Q value. We can drag this component, select it, Control C, Control V, make a copy of it. This case, it gave us a new reference designator. We're going to call it CTB for the B section of the tuning capacitor. And here's our circuit. We're pretty much done. Now we don't want a connection to ground here because the loop didn't have a correct connection to ground. When as I draw, if I want to stop drawing, I just hit the space bar and it'll stop, space bar and it stops drawing. So let's make this be CTB. And there's our circuit. And that should look just like the circuit that we showed earlier. Now let's give a name for the ruse block. And we're pretty much good to go. Now, I don't like the order of which these parameters have been put in this list. SimSmith does it in terms of how I drew my circuit. So the first thing it encountered was CM, so put that first, and it just puts things after that. If I want to control the order, I can just do that. So I'm going to control the order. CM underscore CTA underscore CTB underscore and say that's good. Now I did something wrong here. CBA, where's CBA? Oh, I made a mistake right here. CTB. Now CM, CTA, CTB, and Q. And I can put values in here, say like 20 picofarads, 30 picofarads, and I don't know about this one because that one's going to be a function of CTA. We haven't decided whether this is a gang capacitor where the two values vary at the same time or whether it's a differential where when this one gets larger, this one gets smaller. We'll fix that in just a moment. Let's set this capacitor to vary linearly in 1 picofarad steps. SimSmith is incredibly flexible with doing this kind of stuff, almost to the point where you might think it's a little too flexible. I don't know, but it does. It's kind of cool once you get it all set up. So now we need to be a little bit clever here. So we're going to ask ourselves the question of what kind of a circuit we built here. The circuit we built can be either a differential capacitor or a gang capacitor. So let's ask the question, so let's say diff. So if it's a differential capacitor, what are we going to do? We're going to say CTB underscore, which is the value of the B section of the tuning capacitor, equals. And that capacitor could be anywhere between 12 and 67 picofarads. So we take the maximum value plus the minimum value minus CTA, and then we say that's, if that's the case, that's what we set CTB to be. Otherwise, this is tricky to do on the fly and not make mistakes. CTB equals CTA underscore. Now I have a mistake here. If differential CTB equals 67 picofarads, all right, I did something wrong here. What did I do? Oh, I forgot a semicolon right there. Okay. So now, if we want this to be a little bit larger, this font, we can just click on the plus here and it gets a little bit larger. You can resize these windows a little bit if you'd like. And there's our circuit. So now what I'd like to do is demonstrate the two types of circuits. So let's take this circuit and leave it. We should convert this to be a linear number, not change logarithmically, because we're going to do 0 and 1. So if it's differential, so it is not differential because it's a 0 here. That means as we change this value, notice CTA, when I change CTA, CTB tracks it. I can't change CTB because CTA overwrites it each time, but I can change CTA and CTB tracks it. If it is differential, then they change differently. And when they change in such a way that when the CTA value is 12 picofarads, CTB is 67, and when this is 67, the CTA is, or CTB is 12 picofarads. And that was the 12 to 67 picofarad value that they indicated on the capacitor. Now, I don't know which way this circuit works, whether it's differential or whether it's ganged, but we can simulate both of them by just changing this value, which is kind of clever. So now what do we need to do? We need to just plot that. So we're going to ask ourselves, what range do we want to know this, the frequency range do we want to know what its matching range is? Let's go from 3 to 30 megahertz. Let's change this value to be a different color. And what we need to do is we need to sweep not frequency, but we want to sweep the component values. So we'll go over here to name, and we will sweep a.cm underscore, which is the value of the matching capacitor, and a.cta, which is the value of the tuning capacitor. We'll sweep those, and we will not sweep frequency. So at a given frequency right here, we will look at the matching range. And what we see is this little tiny sliver of a matching range. Let me make sure I have everything correct. And the range we're sweeping is not correct. CTA was given as a 5 to 51 picofarad. Now what SimSmith did was he took the value that I had here and it went into my preferences, which are set to a value of minimum to maximum ratio of 4:1. And it took my capacitor and did twice this value to half that value. So half this value is 10, and the other one, let's look at this one. CM was 10 to 40 because it was set it to 20. Let's put these in a different order. It doesn't really matter. Now, so CTA is 5 picofarads to 51 picofarads. That's CM. CTA was 12 picofarads to 67 picofarads according to the schematic. And we don't sweep this. We can either disable this one by clicking on no, or we can just delete it if we want, and we can always get it back by clicking on name again. But we're sweeping the two capacitor values is what we're sweeping. And we're looking at all the values that this matches to 50 ohms. And that's this little locus of points right here, which is a tiny, tiny section of the Smith chart. This is amazing. It's just all this circuit matches at 10 megahertz. Let's go over here and set these to be linear values in megahertz. And let's set these to be, say, like 10.1 megahertz. So we can move around. Let's go, say, to 7.1 megahertz. We see even a smaller matching range. Let's look at whether differential or ganged capacitor makes more sense. Here's the range for a differential matching capacitor. Here's the range for a gang capacitor. The gang capacitor is a larger range, and that may be more suited to the antenna that we have. We don't know the answer to that until we load the impedance file for the antenna versus frequency. But either way, this tuner, if you just looked at this, you would say, egad, this tuner matches an incredibly tiny matching range of the overall range of impedances that you could possibly match to. So let's put this aside for a moment and let's do the calculation of what the impedance of the loop would be. To solve the next piece of the problem, we need to be able to have an impedance file versus frequency for a loop antenna. And either you can build the loop ahead of time and measure it with a VNA, or you can use a simulation program like EasyNEC to calculate the impedance versus frequency, and that's what I'm going to do. And here is EasyNEC version 5. It's not the current version, but it works just fine. And we'll look at the wires. And EasyNEC's kind of bad. I can't enlarge these windows, and I cannot get EasyNEC to bring windows up in the primary in anything but the primary monitor. So I'll be dragging stuff over. But what we need to do is we need to go down here, and we'll say create a loop. And let's make the loop, this is okay, for wire diameter 0.08 inches is 12 gauge wire. I'll put 5 segments on each side, 16 sides to my loop, which will give me a 20-foot loop circumference. And I'll put the center of the loop, this is where it's sitting here is fine, is 23 feet off the ground. So the bottom of the loop will be about 20 feet off the ground, top will be 26 feet off the ground. And let's see what that looks like. So I do the calculations. The first segment here that was here beforehand, we need to delete. And let's look at the antenna. And what we see is we see a loop with 16 sides on it, and let's feed it at the bottom. So we want to make the source be wire 1 50% of the way in the segment. Right there is where we're going to drive it from. And what we can do is calculate impedance. So what we'll do is we'll say, ask for SWR. Again, drag it over from the other window. I'm going to scan from 3 to 30 megahertz in 100 kilohertz steps. Now, these are way too big of steps if you want to do any kind of tuning on the antenna, but this gives me a matching range. I can see how well the 2 capacitor tuner works with this antenna. So we'll say run. And EasyNext shows that over the frequency range, the antenna has a terrible 50 ohm impedance, which is perfectly fine. But we can look at the impedance if we want to along the way. Or what I can do is EasyNext saves a file called lastz.txt. It saves this file in different places on different machines. You have to go look for it. In this particular machine, it saves it under my username, appdata, local virtual store, program files x86 EZW. Other times it's saved it in other places on different machines, but the file I want to look at is this lastz.txt. And if I just look at this with a text editor, I see that I have a frequency and an impedance. I have more than one impedance. I have an alternate impedance and some other stuff, but SimSmith can read this file just perfectly fine. So we will have SimSmith read that file, and then we can look and see what the estimated matching range for the tuner was versus what the impedance for the antenna was, and see if they need to fall within each other. Now there's just one more step and we're done. What we need to do is load into the load here the scanned file that you scanned with the VNA of the antenna or the simulated file. Since I simulated the antenna, I'm going to load the file. And there it is. Now, as I sweep my frequency, I see the actual impedance of the loop antenna here. And we can compare and see if that matches the matching range of the antenna. So what we're going to do is see what's going on here. We don't want to scan frequency. We want to scan the matching. We want to scan the matching and tuning capacitors. So what we have is a range of impedances in orange, which represent what impedances this matching network can match on from this side to 50 ohms versus the impedance that the antenna is giving us. Well, since this does not fall within this range, this antenna cannot be matched with this circuit at that frequency. Let's move and let's also check and see, look at this range, and as we make this be a differential capacitor, we see the range gets smaller. If it's a gang capacitor, it gets larger, and that's true at all frequencies. The ganged capacitor is the way this circuit really is built. So now let's go and see by the time we get to 9 megahertz, we're within the matching range. The impedance of the antenna is within the matching range of the circuit. So at 30 meters, it's nicely in the range, and at 20 meters, it's still in the range. By the time we get to like 17 meters, it's outside the range. So this antenna can be matched with this tuner on 20 and 30 meters both. So now let's look at the 20 meter match for a moment. What we're going to do is we're going to scan so these values can change up here, and these values can change down here. And what we're going to do is we're going to try to figure out what value here will give us the match at this frequency. What we'll do is we'll look at g.zn and zoom out. As long as this matching range, this is the range of impedances you will get for this impedance right here as we vary these components. And that's the impedance we see over here at the generator. I don't like these being lines. Lines are what SimSmith gives us by default. Sometimes lines are better, sometimes dots are better. I want dots, so let's just make our own function. Once again, same thing as we were doing before. I'm just going to copy this command. I'm going to do Smith of G dot Zn. And if I do that, what I've got is just another set of lines, just like I had before. But what I'm going to ask it to do is give me dots. Now I have dots. I want a dot somewhere in here which tells me each of these dots, say here's one, it's 6.8 picofarads for CM, 18 picofarads for CTA, and of course 18 picofarads for CTB too. And that would give us, that would give us this SWR and this impedance at the generator. I really want some dot that's closer in the center. What I want to do is have more scan points here. SimSmith right now is asked to give me 15,000, 50 times 300, 15,000 scan points, but none of them are giving me a match that's close in here. What's wrong? Well, the preference window said only give me 4,000 points. So even though I asked for 15, I scaled that back to 4,000. I'm allowing 200,000 with my preferences. Your preferences will be different the way you've got the program set up, but you can change those numbers. If I click on sweep, now I get the 15,000. These two are pretty close. So let's take this one and see if we can adjust it. It's 8.7 picofarads and 17.3. So 8.7 and 17.3. And we see a big dot, but the big dot is the circuit analysis using the values in here, not the swept values. And we can turn the swept values off and we'll still see this value here if we want. And that's okay. So we need to adjust these two component values until we get that point moved right to there. So let's adjust this. We see this one following inside. Okay. It doesn't follow the R equal 50 line quite exactly, but let's see what this one does. Okay, I need to increase this one some, and this is where a little practice doing this stuff can make you better. Oh, this is going to be good. Not quite perfect, but it's pretty darn close. Let's I'm just moving the scroll wheel while I'm holding down the shift and the alternate key. There we go. That's a very good match. So 9.223 picofarads for the matching capacitor, 17.18 for both sides of the tuning capacitor, and we've got a very good match. Let's change our generator back to 100 watts, because that's what the tuner's supposedly capable of handling, and we can look at the voltages and currents and stuff. So what we see is this block will dissipate 8.98 watts, or just say 9 watts in the tuning block. 91 watts will be delivered to the load. That does not mean that 91 watts gets radiated, because the antenna has efficiencies that SimSmith knows nothing about. It knows an impedance, but it knows nothing about what fraction of that is lost and what fraction of that is going to be radiated. But it's the best you can get out of a program like SimSmith. You're going to have to analyze the antenna like an EasyNet or something else. But again, your goal is to get as much power into the antenna as you do, and then the second goal you have is to make the antenna as efficient as you'd like. But 91 watts into that's pretty good for this tuner. Now, the next thing we'd like to do is know, what are we doing to these components in here? Well, we can look at the power. We know there's a 9 watt total loss. We can look at the power of each of these components if we wanted to. We can also look at the voltage of each of those components. The voltage is probably a lot more interesting, because at 100 watts, 9 watts in this tuner is not going to burn it up. But what voltages do we see across these components? Well, we can plot these voltages. Let's do RMS which will give me the RMS voltage of, let's say, we're plotting it in this window, so we need to specify the component exactly. So it'd be A dot CM dot small v, which is the voltage across it, and this will be plotted on the square chart on the y1 axis. Okay, now this CTA and CTB. Let's go to this axis, and we need to sweep something here. Let's sweep frequency instead. Then we need to get to 14 megahertz. There we are. And what we see is at 14 megahertz, we see the voltage across the B side of the tuning capacitor is 2.6 kilovolts RMS. And these other two are about equal. The voltage across the matching capacitor and the voltage across the A side of the tuning capacitor are 1.73 kilovolts RMS. And you might got to multiply these by the square root of 2 for the peak voltage. And that's quite a bit of voltage, which is why the tuner needs to have fairly wide-spaced capacitors. And then we can look at the current that flows in these capacitors. The current's kind of an interesting thing because of the fact that it's going to be pretty high. Very similar to what we had before, except we're going to plot I, and we're going to put it on the other axis. Let's put it on the Y2 axis. Turn the voltages off. The axis over here is the Y-axis, and we see 4 amps flowing through the tuning B side of the capacitor, 2.6 amps and 1.4 amps. Now, as we were to lower the frequency and this number would get lower, these currents would rise a lot. Again, I hope everyone who's watching this can appreciate the huge number of calculations involved here in terms of being able to determine both what stresses all the components in the tuner are under, how efficient the tuner is, what the matching range is. This is the kind of stuff that you would never have been able to calculate prior to SimSmith. I've taken this pretty slowly, this video. It's pretty long. I'd appreciate a comment. You don't have to agree with me. I went a little slower this time. If I should go faster or slower or just present the SimSmith file and make it available. I mean, this way you can build the SimSmith file up yourself very easily. I don't know what the right thing to do is. I'm sure whatever I do, somebody's going to like it and somebody's not going to like it. But I hope you've enjoyed this analysis. And this does demonstrate the power of SimSmith. Thank you very much.